Hello, Web Summit. Good afternoon on day 2. It's nice to see a lot of people here again. And hello on Twitch. It's nice to see you online as well. My name is Gabe Hollenby. I am a technical evangelist at AWS. All that means is I'm a software developer who also likes talking to people and building cool demos and learning about new stuff and getting up on stage and getting it to share all of it with you. I think I have the best job in the world, and it's because you give me the opportunity to share what I learned with the world. So thank you for being here today. A little bit about me before we get started. I have been writing all different types of code for all kinds of businesses for a bit over 15 years now. What I am not is an AI expert, and I think that's really important for you to know for this talk, because there's a lot of science that says the best people to learn from are not the experts. It's people who are a little bit further along their learning journey than you are. And so I hope that the way I'm going to present about deep learning to you today is going to be provide a good foundation for you and get you excited to learn more. If you want to follow up with me afterwards, let me know what you thought about this talk or hit me up with any questions. You can ping me on Twitter. It's just my name smushed together. So what we're going to cover today is a few things. I'm going to kick off the demo a little bit towards the beginning, and that's because it's going to take a little bit of time to build. I'm actually going to attempt to train a deep learning model live on stage. And since we don't want to watch some progress bars spinning, I'll kick that off after a few minutes. We'll do some more slides, then we'll come back and we'll see if it worked. Then we'll cover what is deep learning, what is a neural network. We'll look at the code that I use to train the network that you'll see us build. Hopefully, we'll finish the demo, enjoy the cookies that we put in the oven earlier. Then I'll show you how to do it on your own and where to learn more. So before I dig into what is deep learning, I'd just like to know a bit about the audience. Hands up if you consider yourself a developer, you write code. Great. How about the opposite? If you don't write code, keep your hand up. Cool. Don't write code but are interested in deep learning, obviously, or you wouldn't be here. I think there's something for everyone in this talk, so you'll both groups will be happy with what I have to show. So what is deep learning? Simply put, it's just one technique for teaching computers how to do things that are typically easy for people to do, but hard to explicitly program a computer how to do. Self-driving cars is a great example. Sentiment analysis, so Boaz in the last talk was talking about Amazon Comprehend that can do sentiment analysis. That kind of stuff can be hard. I mean, I don't know all the words in English language that are going to mean happiness or sad or frustrated. So it could be hard to program that. Object detection, right? If you take a picture of the Eiffel Tower and try to teach a computer how to recognize that it's the Eiffel Tower or a cat or whatever, that could be hard. I don't know how I would write code that says, look at all these pixels, and if they look like in this configuration, then they're the Eiffel Tower. I really have no idea, and neither does anybody else, and that's why we use deep learning for problems like this. Facial recognition is another one, right? Not just, am I happy or sad, but does this photo of Gabe match this one in the database, or is this, a male or a woman, or how old do I think that the picture is? All of that type of stuff. These are happily in the realm of what deep learning is good at doing. Now, what I really want to impress upon all of you is you don't need a PhD for this. I think that's a common misconception, is like deep learning is the realm of AI and machine learning experts. It can certainly feel that way. I know that 6 months ago, before I had started my AI and deep learning journey, I totally thought this. And I was like, I'm no good at math. My degree is actually in English, even though I've been writing software for 15 years. That's a different story. But I'm not great at math. But you don't need to be. You don't need a PhD in data science. You also don't need a ton of data. In the demo I'm going to run later, we're going to take like 60 pictures live from my webcam and use that. So you don't even need a ton of data. I used to think, oh yeah, image recognition and stuff, that's great for companies like Amazon, where they have a lot of data. But what about me and my startup, or my pet project, where I don't have that massive web scale of data? Can I still use deep learning? The answer is absolutely yes, and I'll prove it to you. So you can start learning it using deep learning for your own projects today. And you don't need a dedicated data science team of experts. There's a lot of nice modern tooling out there, and I'll show you what AWS brings to the table to help you out here that makes that statement true. So this is Amazon Rekognition Image. This is one of our AI application level services. The way this works is you give it an image, and the computer will just tell you back over the API what it thinks it sees in the image. For example, skateboard. If you're sitting in the back, you might not be able to see the results on the bottom of the screen. It says skateboard with 99% confidence score, sport, human. Those are all 99 point something percent confident. Pretty accurate, right? That's great, but it's a really wonderful service, and it's the easiest thing to get started with if you want to do image recognition in your product or app that you're building without even building a model. But customers come to me all the time and they say, Gabe, recognition is awesome, but what if I want it to recognize the things that are important for my business, for my domain? Well, Rekognition currently doesn't offer a way for you to augment it and add to it, but it's actually super easy to train your own custom image classifier yourself. So that's what we'll do. I promise we're going to build and deploy a custom image classifier right now. Fingers crossed. Demo gods, please be with me. Let's see if this works. If not, I have a video, but you won't be as satisfied with the video. So wish me luck. Here we go. So first, we're going to need to classify some images, which means we need images to collect. So switching over here, I have a little web app that I built that is just going to let me type in some images, and it's going to automatically upload them to our object storage service, S3, as I capture them from my webcam. Let me just reload this and see if it's, there we go. Good, okay. So let's give this a dataset name of Web Summit Live Demo. And I'm picking things that I have around. So I've got some cards. This is like my Metro card. So I'm just going to send over here and capture some pictures of a card. All right, let me do some other cards that I have. You can see them, they're actually getting snapped down here. This is my Metro card in Singapore. As you can see, it's got a lot of love. I've been in Singapore for over 5 years now. Here's my hotel room key. Okay. You can see here, we've got 30 total images for cards. I think that's a pretty good number. It's really small, right? It's not thousands of images. Let's do another class. Let's do bottle. Okay, so I've got some bottles down here. Let's do this one. Actually, let's just do just one bottle, and then I'm going to give it a totally different bottle when we test it. So we'll see how that goes. Okay. There's our 30 images of bottle. And let's just, maybe we could do one more if we want. We can do human. It's easy. We have a human present. Why is that not capturing? What do we got? 20. OK, 31. Let's keep it at 30 each. I'll get rid of that one. OK, cool. There's our data. It's already uploaded to S3. It was doing it in the background when we were going on. So next, we have a product called SageMaker. I'm going to tell you a lot more about it later. Right now, all I'm going to do is kick this off by getting a model training going. This is a Jupyter notebook. It's a Python language. It's an interactive programming environment. You don't worry about reading the code right now. I've got the code in slides. We'll go over it more later. What we're going to do right now, let me just make sure that that exactly matches the name of the bucket I was uploading to, because typos kill demos. All right, that's good. So I'm going to just kick this off. All this code is doing, by the way, is things like downloading my images from S3, wrapping them up in a different format that the training is going to want to look at, setting some parameters about my training job, and then actually kicking it off. OK, it's starting the training job. And I'll do one more thing. I'll tell it to deploy after it's done training. OK, cool. We'll come back to this in a little while, and we'll see how it goes. OK, good luck, deep learning model. So this is what we did, right? We put something in the oven. Now we're going to understand the concepts behind that recipe and the cooking I was doing. We'll then read the recipe itself, the actual code. We'll check on the bacon. We'll do our taste test and see if it works. So machine learning, to recap again, It's just computers figuring out how to do things that can't be explicitly programmed. Neural networks are one way to do this. They're inspired by how our brains work. And a really cool thing about neural networks is smart people have figured out that they are provably capable of accomplishing any kind of computational task, given enough memory and compute power. So that means any code that I could actually write, a neural network could also do. That's just the math. People smarter than I have proven it. Deep learning is a way to use neural networks to accomplish this. And it's called deep learning because we layer these neurons, and I'll talk more about what that means in a minute, in several different steps or layers, which allows the computers to learn from complex data without us telling them computers what data is important. So in the olden days, before deep learning, a common thing when we were still doing machine learning was something called feature extraction, where you would have a team of data scientists who were really smart, look at your data sets and go, right, what about this data is going to make it easy for computers to figure out how to do predictions. And they would go through the process of extracting that out. Deep learning skips that step entirely. You just give it your data, and the computer figures out automatically what's important in the data set and does the feature engineering for you effectively. So what is a neural network? It's inspired by how our brains work. And you can think of it like a tree with roots and leaves. So every neuron has a bunch of surface area, or like roots, where it gets stimulated by other neurons that are sitting over here. And then based on how much total stimulation it gets, it's got some tolerance value. And then at some point, it's going to decide if it's happy and if it wants to stimulate neurons further down the chain or not, based on whichever ones are touching its leaves, if you want to think of it like the tree. That's what a neuron is in our bodies. What about a neuron when we talk about for deep learning and neural networks? So I have some videos here. These are taken with permission from a really great math visualization person online, Grant Sanderson. He goes by the handle 3blue1brown. So he has a lovely 3-part series on deep learning introductions as well. So a neuron you can think of as a thing that just holds a number, right? Usually this number is between 0 and 1. But it could be any kind of number. 0.1, 0.9. Now, if we were to classify this drawing of a 9 into an image, to detect it's a 9, how would we do that? Well, it's made up of 28 by 28 pixels, so we have 784 individual pixels. We could treat each of those as a number representing a grayscale value between 0 and 1, okay? So 0 means it's black, 1 means it's fully white. If it's somewhere in between, then it's a little bit gray on the edges of like the anti-aliasing of the image that was taken. That value is called an activation. That's just jargon that you actually don't even need to know for the rest of this talk, but that's neural network lingo for the value of a neuron is what's its activation value. So now if we take that grid of numbers and we flatten it, we can use that as the input for our network. And again, all we have going on here is our original data set, in this case 784 numbers representing our 28 by 28 image of a handwritten digit. And then in this image we have, I think it's 16 and 16 middle layers, nodes in each middle layer, and then the output layer. And every one of these nodes is connected. These neurons are all connected to this layer, and every one is connected to the next one, and every one is connected to the next one. But the goal is you start with your input, representing the shape of your data, and then on the other end is the output representing what we want out of this, right? We want to know, is this thing a 0, 1, or 2, or 3, or 4, or 9, all that. So the goal somehow is to take the numbers on the left and get numbers in the nodes on the far right-hand side where there's a large number where the 9 is and a low number for the other ones. How does that work? How do we get that? Okay, so the neurons are just nodes with values. They're linked together to other neurons with various connection strengths, right? These, we call them weights. Each node value is based on how much of all the connecting node signals arrive into it, plus a little bit of another value called a bias. That's just other neural network jargon. So in this example, there's some other nodes over here, and maybe this is the first layer of the network, it doesn't matter. We've got a signal 1 and a 5 coming into this neuron with weights of 2 and 3, and then there's a bias of -4 on this. So 1 times 2 plus 5 times 3 plus, or minus the 4 plus a -4 is your total value. So that, in this case example, the neuron value is 13. This, in its purest and simplest form, which is enough to understand the basics, this is all deep learning is multiplications and additions, and in a really complicated fashion, in a really complicated network, to get some numbers out the other end. Really, that's it. So, okay, but how does a neural network learn? Well, we could just keep trying random connection strengths between every neuron and each other neuron, right? And then like magically there is one or many solutions of random connection strengths that would end up with the results we want. So we could do that. That's like, a million monkeys and a million typewriters are eventually going to write Shakespeare. But is that how we do deep learning? No, absolutely not. Like, that's a totally inefficient waste of time. There's a much better way. We can actually put some science behind figuring out how to get the magic values for each of these connections and each of the biases. So, if we take another example now and see how we get data through the network, in this case, it's a handwritten 2. So all we can do is change the connection strengths, these weights, and these biases. And the idea is, as this data flows through the layers of the network, what we want is a high value for 2 and a low value for everything else, which is not what we got in our random initial attempt. Right? We got 0.2 for 2, and so some other numbers are higher, some other numbers are lower. Now we can only adjust these weights and the biases to try and change the output. And if we look, we can see that by changing some and changing others, we can make our output layers, the numbers go up or down. But not just that, we can see which ones need to go up a lot, and which ones need to up or down a lot, and which ones need to go up or down a little. For example, you can see that in the final data here, it made a 0.2. I want a really strong value for 2, like 1, as close to 1 as possible. So that one needs to go up a lot. This one down here for the number 8, it was only 0.2. That's pretty low. If it stays at 0.2, and if I can get all of them to like 0.2, 0.1, but then the one for 2 happens to be like 0.8, 0.9, that's good enough. That's enough of an outstanding signal that I'll know that it's probably a 2. So based on how much each of these final ones need to change, you can look back at this step of the network and tweak all of these connections a little bit, and then you can do it again, you can do it again. That's called backpropagation, just jargon for what I just described. And there's algorithms to help figure out how that should happen. You don't need to write this code. There's deep learning frameworks that already do all of this for you. But that's the science and the math behind how that works. So recapping, we're going to start with a randomly initialized set of weights and biases. We're going to send all of our training examples through the network one at a time, or maybe in little batches, but that's an implementation detail. We're going to look at the outputs, and we're going to measure the difference between what we got and what we wanted to see. Then we're going to go backward through the network, tweaking values, and we're going to repeat this over and over and over again over many cycles or epochs until we get a network that performs well for our data. We have to be careful, though, because if we only give it all of our data and train it on it, then we might overfit our model. What that means is the network might just get good at memorizing the data we've given it, but it won't be good at generalizing the observations it needs to for new data. So we also want to run some validation examples through the network as we're training it, that it wasn't used for the training steps to score a model in a particular iteration, and see if we're at a point where the model looks good, where we've got a high trained model score, and it also passes the test really well with images that were not used for our training, for example. Then we'd be good. Now, this technique will work fine. It will work for recognizing handwritten digits, for example. And you can make a network just like the one I drew up there before that will recognize images pretty darn well. The performance is very high for handwritten digits. But there's another piece of cool technology that I want to share with you, because it's also how image recognition works better than just what I've described. And it's something called a convolution. Now that's just more jargon. What it means is, let's examine neighboring pixels together. Because when you're doing image detection, for example, the context of the image, you have a 2D context, right? So if we just flatten this out from the beginning into one big long list of numbers, we lose the relationship between surrounding pixels, and that could be very helpful in helping a computer figure out what features are important and what they're not important. So what we do is we make a little map, and that map is a set of values that we're going to use for any given pixel. So here, we're looking at this pixel, and it's going to say, okay, take the pixel for each surrounding pixel and modify that value by some amount, add them all up. So this is just doing a little bit of matrix calculations here, but it's still just pretty simple math. At the end, you get a new value for that pixel. And you just slide that little square all along the whole image until you've got something else. And you can do super cool things with this very, very basic technique. Okay, so for example, with this style of this mapping, what we call a convolution kernel, just the word for it, you get something that finds the outlines of images, the edges of images really well. Like that's how Photoshop does like sharpen, right? I never knew that, but it's super simple actually, right? So there's sharpen. That's a slightly different image kernel, but that makes some features more apparent than others. And so based on different values for each of these, these 9 pixels in the grid that you use for the convolution kernel, you can extract different features. Find the right edges of an image, find the left images, find the outline. So you can add a step into your deep learning, call it a convolution, where the training will automatically figure out what are the right values for that convolution kernel as well. So you don't have to think of them either. The computer learns, because different images might benefit from different types of convolutions. So if you've heard of convolutional neural networks, that's what this is. It's a neural network that also uses this convolution technique to help improve the signal as it's flowing through the network for the relevant parts of the data. Now, this is what is so cool about convolutional neural networks. As we layer these layers together of the deep learning network, it gets smarter and smarter. So in the first layer of a convolutional neural network, it's able to figure out things like edges, contrasts, or similarity. By the second layer, it can figure out where there's lines in an image, where there's circles, gradients in an image. It's learning these things automatically. By the third layer, it's figured out complex patterns. It's figured out that there's like text in images is a thing. It's figured out that like human body shapes is a thing that it sees. And by like 5 layers, it's good enough that it's like, yep, that's the head of a dog. That's a bicycle wheel. That's the center of a flower. Or these are the eyes of an animal. And right, that's just successive application of this style data connected to this style data connected to this style data through the network, right? This is the feature engineering that the network figured out automatically for us. So, making our own custom image classifier in 21 lines of code. How are we going to do it? How did I do it? Hopefully, if the demo works. So, AWS has a lot of AI-related services to help you out in whatever level of the stack you're comfortable working. Because this is an introductory talk, I'm not going to spend a lot of time talking about the frameworks and interfaces, but you may have heard of some of these things like TensorFlow, or PyTorch, or MXNet, or Keras, or Gluon, or Caffe. These are all deep learning frameworks and interfaces that make it very easy to write your own networks and train them. So this is really the realm of where if you're lucky enough to work with specialized data science teams, they're probably working here. But if you're like me and you don't have that background and you still want to get started building your own model, you can move 1 layer up the stack. 1 layer up, we have a service called SageMaker. This is the one I'm going to demo for you. SageMaker makes it really easy to build your own models without having a lot of deep learning modeling expertise on your own. At the top level, we have services you're probably already familiar with. We've talked a lot about them during today already, and you'll continue to hear some of these for the rest of the day. Things like Lex for chatbots, Polly for doing lifelike speech from text, Rekognition you saw me talk about, these kinds of things. So we have a really comprehensive suite of services to help you wherever you are in your deep learning journey and whatever you're trying to get done. But let's talk more about SageMaker. So SageMaker makes it very easy to build, train, and deploy your models. The kind of tagline of SageMaker is, our goal is to put the power of machine learning in the hands of every developer. And when I first heard that, I thought, oh, that's like a really lofty goal. That's like lovely marketing speak. But I can tell you now, and not just because I work for AWS, but honestly, my own personal experience was, after I trained my first model and saw how easy it was to do with SageMaker, I went, yep, it's true. I really did feel like I can make models now, and so can all of you, and you'll see how. So SageMaker, the 3 kind of pillars, It can let me build my models, so it will host a Jupyter Notebook for you. Python is kind of the lingua franca of deep learning and machine learning. So they host a Jupyter Notebook for you automatically. I'll show you that again if you want to see it. There's a lot of templates for common machine learning applications. Built-in high-performance algorithms is the real key for me. So if you want to train an image classifier, SageMaker already has a network built for you that all you need to do is feed it your data. And that's what I'm going to use in my demo. If you want to do like machine translation, or you want to do anomaly detection in time series data, all these kinds of problems and a lot more, there are already industry-known algorithms out there in the world, network designs done that we've wrapped up nicely for you, where all you need to do is give us your data, not give us your data, but you know what I mean. Pass your data through to SageMaker. We don't see your data, and have it train your models, and then you can host your model. So that's what we do here. We build, pass it our data. We can tell it to train. We wait a little bit. It's probably done by now, and then you can deploy. So another part of building your own models is that's all well and good to have your model trained, but how are you going to use it in production? You probably want a highly available endpoint if you're going to deploy your model to the cloud, so that other services that you're building can call that model and have it used reliably. That can be a pain in the butt to host. We handle that for you, so it's not a pain in the butt. It's dirt simple. You might want to A/B test different models to figure out which one is doing better for data that's coming through in your domain. SageMaker handles that as well. And of course, all the features you come to expect, like auto-scaling. So if you have a lot of demand in your hosted model on SageMaker, you can automatically spin up more servers behind the scenes to manage that load for you, so you don't have to over-provision. OK, now we're going to look at some code. Most of the hands in here were developers, so I hope you're OK with this. If you don't know Python, you're still going to be able to follow this, I promise. So what do we do? Our first step was not even code, right? It was just, let's get our images into different folders that represent the classes we care about. That's what my little app did when I was taking screenshots with my webcam. So we've got some top-level folder, and inside there we have folders representing each class. We have a bunch of JPEGs inside each of those. Easy. Next. OK, this is that step I told you about where we want to split our data into training and a test group. I was learning about deep learning before, and I thought, oh, OK, that sounds good. And I spent time actually writing my own script to do this, which was silly because there's tools out there that already do this, and there's one that's even included automatically in the Jupyter instance that SageMaker hosts for you. So again, like my advice is, as developers, we always think, oh yeah, I can do that. I can write some code for that. That doesn't mean you should. Spend like an hour, skim through all the docs, and you'd be surprised what you can save time by not having to implement yourself. So there's a script called im2rec. It's for like images into rec. So SageMaker wants to see your images in one of two different formats. One is just like a manifest file that says, it's like a CSV that says, OK, this image inside this directory path, it belongs to this class. Next, next, next. The other format, which is called record.io, says it's one big file. And in that one big file is wrapped up in that is the binary data for all of your images and what classes they belong to. And you can use either. I'm showing you how to do both here because for certain applications, you might benefit from converting it into that record.io format. The im2rec script does both, right? So first, all I'm doing is saying im2rec, make me this LST file, that first manifest file I was talking about, recursively crawl through to the directory of classes of images. Don't touch the images at all. They're already in the size I want. Keep 30% for test. Use 70% for training. This is the prefix name for the output, labeled classes. This is the directory that I want you to look at, classes. That's it. Next, I'm going to use the same tool. I'm going to say, use the LST file you just generated and actually look at all the images on disk and wrap it up into one big record.io file. OK? Or two files, rather, right? One for training, one for validation. Finally, I'm going to upload these to S3. If you can't see at the bottom, all this is doing is saying, I'm using the AWS command line interface to copy the record.io files into a bucket. And so that's so I can tell SageMaker, when I tell it to train my model, you can pull my data for training and for validation from this S3 bucket. OK, now we're going to create an image classifier. So we say import SageMaker, and we're going to import a particular image classifier from Amazon Estimator, get image URI. and that's to get the Docker image. So this behind the scenes, this all works with Docker. You don't need to know Docker at all in order to use this. I'm just letting you know that's why it says get image URI. So what we're doing here is we're going to say, OK, in my Jupyter notebook, I'm going to get an execution role that SageMaker can just run on. This is so that you can configure tightly framed permissions so that SageMaker doesn't see all the data in your AWS account, but only the stuff relevant for the S3 bucket that it's going to train from. That's a good practice. So you can lock it down that way. Then I'm going to get a SageMaker session just from, this is just like a programmatic thing. And then this training image is not an image like a JPEG, it's a Docker image. So I just say, OK, get me the image classifier ready to go Docker image that Amazon already built for me. Now I'm going to make an image classifier. So make me instantiate this estimator class for me using that training image and the role. I want one training instance. So this is fine for the 60 images in my demo. But if I had a ton of data, I could say, I want to use 20, 50, 100, 1,000 instances for training. So parallel training on big data sets is as easy as just changing that number. OK, next, what instance type do I want to train on? So AWS has a lot of different compute options available for different types of workloads. We have some classes that are really good for machine learning. The P3 instance class is our latest and most powerful classes for machine learning. I'm using the lowest powered P3 instance in this example, a 2x large. That costs about $3.06 per hour total, but we're not paying for it all the time. We're only going to pay for the time we spent training the model. And I'll show you that as well. Where do I want the output of the model to go? Another S3 path. And finally, just giving it the session that it got from this line above. With that in place, we're going to give it some parameters about training. This is things like, how many images are there in the training sample data set? So I can derive, how many classes are there? I can derive this by just introspecting my file system, right? Looking and seeing how many files are in each of those folders. So that's just code that does that. Finally, we're going to pass those parameters in. This is the key. Use pre-trained model equals 1. So remember when I told you don't need a lot of data to do machine learning and deep learning? This is true if you take advantage of something called transfer learning. Transfer learning is just jargon that they use in the industry to mean take a network that was already trained and then just get rid of the last layer where it's figuring out those finally extracted features like dog eyes and bike wheels and the weights between that layer and the final output layer. Just get rid of that last layer and figure out what those new connections should be for the data set that I have. So there are pre-trained models out there already that are great at recognizing tens of thousands of different types of things in the world. We're going to take one of those models and just get rid of that last layer so it doesn't know about dogs and cats and fish anymore and whatever else. But it knows how to find edges and how to find animal eyes and bike wheels and all that stuff. And it's going to use all of that data to figure out, in this case, what were cards and what were bottles and what were humans. What's the shape of my images? 3 channels and 224 by 224. How did I know to make my image this size? I looked at the documentation for the image classifier built-in algorithm in SageMaker's docs. It's actually very clearly stated there. So that's why I didn't need to resize it in my previous step. I had my webcam already configured to capture JPEGs at 224 by 224. OK, we pass all that data in. Then we give it the training data, right? Where in the bucket should it find this data in the validation data? OK, that's just setting up these two values for this object or this dictionary that I then tell. This is the magic line. OK, image classifier, go and fit, train the model using the data inputs that I have here and log some output for me because I'm interested in seeing what the output is. Finally, if you can't see this at the bottom and the back, it just says image classifier.deploy. After I'm done training, I'm going to deploy that. And this is going to give me an initial instance count of 1. And I don't need this to be a beefy instance. I'm serving a model I already trained. So instead of using that super powerful P3 instance class for training, I'm going to use a really low-powered T2 medium instance for serving my model, because it doesn't need to be super computationally strong, or it doesn't need to have a GPU even. You only need GPUs mostly for training. And then, if I wanted to classify an image using our deployed model, this is how we could do it in Python. So I have a function here, classified deployed. I give it a file name, and I tell it the classes that were included. Or in this case, I have them Probably should remove this line. I should take the classes in from the function call and not have it there. Excuse me for that. But anyway, at the end of the day, this is really the magic. We're going to say image classifier.predict, give it a payload. That payload is basically just saying, here's the content type for this. It's application/ximage, and here's the bytes of the data. This is the same thing you could do from any other language. You could do it from curl, et cetera. You're just taking your JPEG from wherever it is in whatever programming language and calling a RESTful endpoint with this, right? I'm just showing code on how to do this with Python. But the whole point of training our model and deploying it to an HTTP endpoint is it's available for whatever language we want to work from. OK. All that code we just saw is what I ran in my Jupyter notebook. If the gods are with me, we can actually test this out now. This is the moment of truth. Let's see. Fingers crossed. OK, here's the logs from when I said training. I'm not going to read every line of this because I will run out of time. But what you can see here is, OK, there was some preamble stuff. Oh, I'm getting started. I'm booting up with some data. OK, but check this out. As we keep going, we can see that it starts training. And it'll tell us the different epochs that it's training through and how accurate it is, different values we can see. OK, its training accuracy for its first run through epoch 0 was really low, only 0.51. Then after the second epoch, epoch 1, look at that. After one epoch, it was one cycle through my image, it was already up to 0.9. Now, you can tweak things that I haven't explained yet because it's kind of like the next level. And I didn't want to get stuck in the weeds, but you can tell it, there's other parameters you can give it when you say train, when you say image classifier.fit. You can tell it how many epochs to run for. The default here is 30. I could probably get away with 5 here, or 10, but I left it at 30 because I also wanted to show you that, like, in most cases, it doesn't matter. It might, and you might end up with a model that overfits at some point, but for this example, I know it won't, or it never has in any of my previous attempts, so I didn't want to cloud my previous slide with extra parameters you didn't need to accomplish it. You can also tweak something called the learning rate. That is a value that says, when I'm tweaking the values in my neural network, when the algorithm is going and saying, all right, this network was crap, I need to tweak my weights and my biases, how much do I nudge them by? That's called the learning rate, and you can pass that in too. So when you hear people talking about like tuning their models or fine-tuning their training, what they're doing is changing these values and running the model training over and over and over again until they can get a model that performs better. All of these things are called hyperparameters, right? This is data for the model that's not the actual image itself. So it's parameters about the parameters, so they call it hyperparameters. It's a funny word. I don't know why they don't just call it like extra arguments about training. But anyway, those hyperparameters are what you can fiddle with. You don't need to fiddle with them, though. You can also, SageMaker has the ability of figuring out the optimal hyperparameters for you. So there's a hyperparameter optimization feature. I don't have time to show it to you, but you don't even have to play with that stuff yourself. You can have the machine figure that out for you as well. Anyway, what we can see is at the end, it deployed our model, or it finished training the model. And we can see billable seconds, 176. OK, well, this machine was $3.06 per hour divided by 60 minutes, divided by 60 seconds, times 176 seconds. That was 15 cents of training time. So training models in the cloud can be very affordable. Side note, you might actually get even lower training times with a more powerful instance that costs more money per hour because it's able to crunch through your data in less total time. So don't think, I'm a startup, I'm saving money, I should always use the lowest time. If you're comfortable, fiddle around. Try one of the bigger instance types and see, you might end up saving money with a more powerful instance as well. After it's done, I said, OK, deploy my endpoint, and it deployed. And so now I can say, here is my endpoint name. And I wrote another web app that will capture data from my webcam. Let's refresh this. And it just says, OK, what's the SageMaker endpoint name? What region is it in? I happen to do this in the US West 2 region, that's Oregon. And what were my class labels? I can go back here and I can look and see. My labels were bottle, card, and human. All right, here we go. What am I? Hopefully I'm a human. Yep, so it says human. You can't see at the bottom, but it says 0.96, so that's good. Let's keep going. Let's try a bottle. First, let's try a bottle like, okay, great. Well, maybe you just memorized me, right? So I'm going to use an Evian bottle. Sorry for it's not brand placement or anything. But I trained with this bottle. Now we're going to see if it can recognize this bottle, which was not in the training data at all. Let's see. Yep, bottle. Now you can see it's a little bit low, 0.50, but it still thought it was a bottle, which means it thought it was a bottle more than it thought it was a human or it thought it was a card. Obviously, with more data than 30 images, it would be even better. But the point is, even with only 30 images per class, it was still good enough to get that right. Let's try a card. So again, with the cards, I only trained it with the back of my hotel room key, so I'll use the front this time. Let's see what that says. Card. So it really works. You don't need a lot of data. You don't need a lot of time. If we go back and we look at the actual total time taken, the training time for the billable time was 176 seconds. The total time for this was 5 minutes and 43 seconds for this step. Why the difference? Because behind the scenes, what this code was doing was provisioning a Docker container onto a P3 instance somewhere and passing all my data, or getting my data ready to pass through. That just takes a little bit of time. So most of the time you spend in training for that step isn't actually the time that it's crunching through your data. It's just getting ready and provisioning. So total wall time, 5 minutes, 43 seconds. Total billable seconds, 176. So it's a big difference there. And finally, deploying. Deploying took about 8 minutes. So that's a little bit longer because, again, what's happening behind the scenes? It's setting up a highly available web server instance with all the infrastructure necessary behind it to monitor it, to do auto-scaling if I needed auto-scaling. I mean, I'd have to configure that separately, which I didn't do when I kicked it off, but setting all that infrastructure up does take a few minutes to get done, but it's not something you're going to do all the time. So total time for this demo, about 15 minutes. And again, I could deploy more things, or I could classify more things from Python here, but you saw me do it from the webcam, which is good enough, I think. Okay. So, I hope that was impressive. I was impressed at how easy it was to do when I was learning this. All these people are impressed too. More machine learning is running on Amazon Web Services than anywhere else. This is not even all the customers, obviously. There's a lot of customers that are running machine learning workloads on AWS because we have great instances, we have great tooling at every layer of the stack. So I strongly think you should consider running your machine learning workloads on AWS as well. Okay, a couple of detailed use cases real quick. Expedia, they've got over 10 million images from 300,000 hotels, right? The problem is some hotel images are awesome and some are not so great. And when you're trying to get people to book your hotel room, you want to show good images, not bad images, right, from customers. If you want to show real customer photos of the properties and not just the professional ones, right? So they used a pre-trained CNN in a similar fashion to what I showed you today, the same concept, using 100,000 images that they had. And that lets them figure out the best images available for each of their properties. So you now have the same capabilities. You can go away for your startups and do the same kind of thing with the demo code that I've shown today. Grammarly is another cool example. So I see their ads on YouTube all the time. It's a cool product. As you're typing, it suggests ways that you can improve what you're writing. They like using AWS and SageMaker because they can distribute their training, right? So as you get more and more data, you might not be able to get away with one training instance anymore, but parallel training is as easy as making that number one into a bigger number with SageMaker. I think that's a real benefit as well. Okay, so where can we learn more? I have a few places to recommend to continue your learning journey after today. First, those two little animated video snippets I showed, again, they're from a guy online who goes by the handle 3blue1brown. It's an awesome series on YouTube called Understanding Neural Networks. It's about 60 minutes total watch time across 3 videos. Next, if you want to invest a little bit more than an hour, I've had a lot of great learnings out of Fast AI. This is an online course for deep learning. There's actually several courses. It's all free. The one deep learning course that I recommend, it's Practical Deep Learning for Coders, I think is what it's called. It's about 14 hours of total content, but it's not made to just run through 14 hours of videos and suddenly you're an expert. Obviously, real learning comes from getting exposed to information and getting your hands on and practicing. Finally, there's a great book online available for free called Neural Networks and Deep Learning. So if you want to get into more details, a little bit more of the math and concepts, that's a lovely resource. Obviously, you should definitely use SageMaker for when you're ready to train your models yourself. And finally, all of these demos are already on GitHub, the code for my Jupyter notebooks. And if you like my webcam classifier or my webcam inferencer, that's already on GitHub too. So have at it. And again, leave you with this. Machine learning really is for everyone. Don't let anyone tell you otherwise. I'm curious, what will you build? Please let me know. Keep in touch. Again, if we haven't scanned your badge, make sure we do. So we can, and all of you out there as well, so we can send you AWS credits, and also you get copies of all the slides from today. Thanks so much. Please keep in touch and let me know what you thought of today's presentation.